Hi everyone. In this video we're going to talk about transformations. There's going to be a lot of information for transformations, so you might want to get your note-taking equipment handy for this one. Uh, we're going to be taking our reference graphs and transforming them. And I want to explore these different transformations. There's a number of them. The first one is f of x plus c. Uh, and this notation means we're going to start off with one of our reference graphs, like absolute value of x, but it could just as well be cube root of x. It doesn't matter. We can apply these transformations to any of our reference functions, and we will be. So let's just start off with absolute value of x. We know this has reference points negative 1, 1, 0, 0, and 1, 1. But then we see some sort of transformed version of this, like y equals absolute x plus 2, or y equals absolute x minus 3. So let's take a look at these on our graphing calculator. So here's absolute value of x, and I'm going to do zoom, and then scroll down to number 6 that says standard, zoom standard, and hit enter, and I see our absolute value of x. Well, I don't see our absolute value of x graph. Hold on. There we go. Our absolute value of x graph, passing through negative 1, 1, 0, 0, and 1, 1. But now I want to graph y equals absolute value of x plus 2 and see if we can say something about the relationship between this new function and our original reference graph. So down here in y2, I'm going to do absolute value of x plus 2. Now, where do you find absolute value? It's here under the math button, math, and then not here, but here in num for number. There's ABS for absolute value. So I want absolute value of x, close parentheses, plus 2. Okay, so let's graph. And what do you notice? Well, I notice a couple of things. These lines are parallel, and this one now has its vertex at 0, 2. The original one had a vertex at 0, 0. What did I do to this original graph to get this new one? And the answer is, I better think about that. Okay, so let's take a look at this other one, absolute value of x minus 3, math, absolute x, close parentheses, minus 3. All right, there's absolute value of x minus 3. What happened to this one right here, the middle one, absolute value of x graph, to make this one absolute value of x minus 3? Or what happened to this absolute value of x reference graph to make this absolute value of x plus 2? And it looks to me like when I have a number outside of the function, like this plus 2 or this minus 3, that causes a vertical shift. Either the graph went up or the graph went down. It maintained its same shape, it just all shifted up or all shifted down. And so we're going to say that when we see this, that this is a vertical shift. Now, what do we have to do to these reference points to make this new graph? Does this plus 2 affect x values or y values? Well, when I looked here, I saw that this ordered pair 0, 0 became this ordered pair 0, 2. The x values didn't change at all. The y values did. I see this point 0, 0 became this point 0, negative 3. The graph shifted down 3 places because of this minus 3. So I'm going to add negative 3 to all the y's. I'm going to add 2 to all the y's. That's how I'm going to carry out these transformations. This shifts the graph down, this reference graph, down 3 places, and I'll do that by adding -3 to all the y's. This shifts our reference graph up 2 places, so I'm going to add 2 to all the y's. So, vertical shift up or down C places. Okay, so how will we carry out this transformation? Well, that's no problem at all. We're going to start off with our reference graph and our reference points. Our reference points, -1, 1, 0, 0, 1, 1. And if I want to graph y equals absolute x plus 2, I have to add 2 to all the y values. So my new points will be -1, 3, 0, 2, 1, 3. And making a graph of this, well, I already know the shape of absolute value of x. This is the vertex point, is just going to be 0, 2, 1, 3, and -1, 3. Remember, we need to label these points on the graph, not merely nearby. All right, don't forget the appropriate shape for this absolute value. So, what about y equals absolute value of x minus 3? Why don't you pause the video and see if you can graph that one by hand. Come back when you're done. Okay, so for this one, I'm going to start with those same reference points from the reference graph. But because I see this -3, I'm going to add a -3 or subtract 3 from all the y values. So my new points will be -1, -2, 0, -3, 1, -2. So my graph, 0, -3, 1, -2, and -1, -2. And the same shape. No problem graphing these. I'm not going to use a t-chart. I'm not going to just draw something that looks like it's been shifted down. I actually have to label points on that graph. Yeah, just no problem. So when I see y equals f of x plus c, and that plus could be a negative too. When I see absolute value of x plus, or f of x plus c, I know that that's a vertical shift up or down c places. And I'll carry out that transformation by adding c to all the reference points. That's our first transformation. Well, what happens if that c value isn't outside of the function, but instead inside of the function? What if we have f of x plus c? What if our function looks like this? So again, I'm going to work with y equals absolute value of x because it's a simple graph and we're pretty comfortable with it. And then I want to look at some transformations of that graph, like y equals absolute x plus 2 and y equals absolute x minus 3. So now I have a plus 2, but it's inside of the function. I have a minus 3, but it's inside of the function. So let's go back to our graphs. And here, go up. Here I want to take out that parenthesis and put it over here. And again, we're going to start with, we're going to start just by looking at our reference graph. Here's our reference graph. And now we'll graph one at a time these transformations. We've got absolute value of x plus 2, which we'll graph first, and then we'll come back and graph absolute value of x minus 3. All right, so let's turn that one off and go up and turn that one on. No, I don't want shading. Why are you way over there? So many choices. There we go. And here. Great. Okay, turn that off and we'll just graph absolute value of x plus 2. All right, now I see my reference graph here with its vertex at 0, 0. Look where this one is. Now, a lot of students say, plus 2, shouldn't I move that way too? But this moved that way too. This moved left too. Huh. Well, I wonder what's going to happen when we do this one. Let's take a look. We'll turn off the middle one, turn on the last one. There's our reference graph. Where is our middle, our third one? Oh, I turned it off. There we go. Huh. I see the vertex at 0, 0 on our reference graph, but our transformed graph has a point at 3, 0. So it looks like our graph, this one, moved this way 3 places. This was right 3. And so I want to say something about transformations inside the function. Inside is opposite left. You know, when I saw f of x plus c, I did what I saw. I saw absolute value of x plus 2. I added 2 to the y's. But now when I see this, and I see that the graph shifted left 2, that's not going to affect y's like this transformation outside the function. It's opposite land, so it affects x's. And what do we do to the x's? Did we add 2 to all the x's? Well, if we added 2 to all the x's on the reference graph, this vertex would be over here at positive 2. But when we graphed it, we saw it over here at negative 2. And so I want to say that this is also opposite. If I want to go left 2, I have to subtract c from all the x's. Here I'm subtracting a negative 3 minus a minus, which means plus 3, and so I go this way 3. Here I'm subtracting 2, which means I go this way 2, left 2. So my rule is I'm going to subtract c from all the x's. Okay, there's our second transformation. How do we carry it out? No problem. We'll start with those reference points, negative 1, 1, 0, 0, 1, 1. And when we think about graphing this, y equals absolute value of x plus 2, I know that inside affects x's and is opposite land. So I'm not going to add 2 to all the x's. I'm going to subtract 2 from all the x's. So my new points will be negative 3, 1, negative 2, 0, negative 1, 1. Plotting those, no worries. There's negative 2, 0. Here's negative 1, 1. Here's negative 3, 1. Ta-da! There's my transformed graph. That's how I graph this. I'll take the reference points from absolute value of x, and I'll apply this transformation to them. We're going to be using transformations all year long, so you can't hide from this. And if you're moving on to the next math class, guess what? You're probably going to be doing it there, If it's calc, you're definitely going to be using transformations. So let's make sure we get these transformations and are comfortable with them. Again, we've got two of them so far. We've got f of x plus c. That's a vertical shift. Add c to the y values. And then we've got f of x plus c. That's a horizontal shift. And what we're going to do here is subtract c from the x's. And when I say the y's or the x's, I'm talking about the y's and x's of the reference points on the reference graph. So let's think about this function, for example. Y equals square root of x. If I have y equals square root of x plus 4, I'm going to add 4 to all the y values of square root of x. These were our reference points, and so I add 4 to all those y's. And so now I've got 0, 4, 1, 5, and 4, 6. And I see that my graph was just moved up 4 places. No longer at 0, 0, now at 0, 4. No longer at 1, 1, now at 1, 5. And finally, 4, 6. Remember to label the points on the graph. If you just leave them off to the side and don't put these points here, I mark it wrong. Okay? So that's that transformation. But if I saw y equals square root of x minus 4, I know inside is opposite land. And so this doesn't go left 4. This goes in the opposite direction. This goes to the right 4. And what am I supposed to do? Subtract c from the x's. So I'll start off with my reference points. And I'll subtract a negative 4 from all the x's. Subtract a negative means add 4. And so I end up with 4, 0, 5, 1, and 8, 2. Same shape. 4, 0, 5, 1, 8, 2. And there's our graph. We have 2 transformations now. And again, the cool thing about these transformations is they work on anything that's a function. So all those functions that we had for reference graphs, yep, these transformations will work on any of those and anything else that we learn as a function along the way. We'll have lots of functions, and so we'll be applying transformation lots of times. Okay, next, I want to look at c times f of x. Y equals c times f of x. And here, I'm going to define a new, no, I guess we can use the same f of x. We've got y equals absolute x, and now how about y equals 6 times absolute x, or y equals 1/2 times absolute x. Let's see what happens when we graph these. So I'll come back here, and I'll turn this into 6 absolute value of x, and turn that one off for now. Insert 1/2 absolute value of x. All right, any thoughts on what it might be? Can you take a guess? What do you think is going to happen? Well, I noticed these transformations are outside the function. And when they were outside before, they affected the y values. Will this shift the graph up 6 places? Let's take a look. If I hit graph, there's my reference graph. Ooh! And there's 6 absolute value of x. And you know what I notice? This one still passes through 0, 0, just like this one. So the graph wasn't shifted up 6, but look, this is so much steeper. And so what's happened is I multiply the y's by 6 here, which I guess means here I'm going to multiply all the y's by 1/2. So instead of being really steep like 6 f of x is, I'm wondering if this other one will just be flatter. Let's take a look. There's our reference graph. Oh, look. Still passes through 0, 0, so no shifting has occurred, but instead of being up here, I'm now half as high over here. And so I want to multiply the y's by 1/2. So when I see this transformation, we call this a vertical stretch or compression. How do we know when we're going to have a stretch versus a compression? Well, we get a stretch when c is greater than 0, and we get a greater than 1, and we get a compression when c is between 0 and 1. This number is between 0 and 1, and so my graph compressed vertically. This number is bigger than 1, so my graph expanded vertically. Okay, so we're going to start with those reference points for absolute value of x. Remember those, negative 1, 1, 0, 0, 1, 1, and we're going to multiply the y's by 6. So let's multiply these y's by 6, times 6, times 6, times 6, and we end up with negative 1, 6. Notice here, 0 times 6 is still 0. That point doesn't change. And then finally, 1, 6. So our graph, 1, 6, 0, 0, and over here, negative 1, 6. Okay, so that's when we have c times f of x. That's going to be a vertical stretch because our c value was bigger than 1. And here when we have a c value between 0 and 1, that's going to be a compression. Instead of multiplying all the y values by 6 to do this, I'm going to multiply all the y values by 1/2. And so we end up with negative 1, 1/2, 0, 0, 1, 1/2. So this is 1, 1/2, 0, 0, and negative 1, 1/2. All right, that's how we'll graph those transformations. Next, our fourth transformation, f of cx. Now, it's really hard to see this transformation when we use absolute value. It certainly works with absolute value, but it's harder to see and recognize. So I'm going to define a different function here for f of x. Let's say f of x is this polynomial function, x plus 1, x minus 2, x plus 5. And where does this function have x-intercepts? Okay, inside his opposite land at positive 2, at negative 1, and at negative 5. Let's graph that. Okay, so I'm going to go over to y equals, and I'm going to put in x plus 1, x minus 2, and x plus 5. Okay, so we're considering this our reference graph. And I want to do f of 3x, or I want to do f of 1/2 x. Now I see that these are inside the function. And before, when we had f of x plus c, when we were inside the function, did that affect x's or y's? That affected x's. That's right. So we're going to be doing something to the x's here. Well, let's see if we can figure that out. I want f of 3x. Okay, so that means I need to replace all the x's with 3x's. Let's see what happens when we do that. Boom, boom, boom. Okay, so we've got 3x plus 1. We've got 3x minus 2. And we've got 3x, oops, plus 5. Okay, and let's start off by just looking at the reference graph. It's a function, but it's not one from our reference function list. And we'll hit zoom 6. And I see that I probably want to change my y values on my viewing window a little. I want to go a little higher and a little lower. So how about negative 20 to positive 20 in steps of 5 graph? Okay, so that's my reference graph. It's a function, and now I'm going to carry out a transformation of that. Now I'm looking at 3x plus 1, 3x minus 2, and 3x plus 5. Now notice here, I can see the x-intercepts. They're located at negative 5. That comes from that one. They're located at negative 1. That comes from that one. And they're located at positive 2, and that comes from that one. Okay, so let's graph this transformed version now. What? Look, there it is. It's squeezed in. And I notice I'm going to push the y max a little higher. Y max to 30. Okay. So there's my reference graph. And here's my transformed graph. So, did the y values change? Look, here's the maximum y value here, and it's the same maximum y value here. Here's the minimum y value here on the reference graph, and here it is on our transformed graph. The y values aren't changing, but the x's sure did. Look, this one is no longer at negative 5. It's now squished in here. And this one is no longer at negative 2. It's squished in even further. And this one that used to be at positive 2, it's now over here. So when I see this transformation, I've got a horizontal stretch or compression. Kind of like playing the accordion, right? I'm stretching the graph, I'm squeezing the graph. I'm squeezing the graph this way if C is greater than 1. But I'm stretching the graph this way if C is between 0 and 1. Now, that's the exact opposite as it was when we were talking about C times f of x. Remember this one? This one was a stretch for C bigger than 1 and was a compression for C between 0 and 1. Okay, so that's vertical. Again, inside affects the x's, outside affects the y's. Inside is opposite length, so on the outside we knew this. On the inside, that switches and becomes the opposite. So now we have a compression when C is bigger than 1, and we have a stretch for values of C between 0 and 1. So when I see this, what am I supposed to do? Well, this number is bigger than 1, so I know my graph is going to squish in. And if my graph squishes in, that means I'm doing something to the x values. What is it that I'm doing to the x values? I'm going to divide the x's by 3. So that x-intercept that used to be at negative 1, well, I've got negative 1, 0, and here, this was an x-intercept at 2, I've got 2, 0, and here this was an x-intercept of negative 5. and so negative 5, 0. These are my intercepts on the original graph, but now I'm coming back and doing this transformation. I need to divide all the x's by c. Divide the x's by c. Okay, so my new points would be negative 1/3, 0, 2/3, 0, negative 5/3, 0. My graph will look like that same polynomial shape. It's just got these other x-intercepts. We've got negative 5/3, we've got negative 1/3, and we've got positive 2/3. And there's our shape through those points. I think it's always nice if you label a y-intercept with polynomial functions like this. And remember, our function was x plus 1, x minus 2, x plus 5. How do I find a y-intercept? I set all the x's equal to 0. 0 plus 1 is 1. 0 minus 2 is negative 2. 0 plus 5 is 5. And so I end up with 1 times negative 2 times negative 5, or 0, negative 10 for the y-intercept. Now, this is just a compression, a horizontal compression of our reference graph. Remember, our reference graph passed through these points, 2, 0, negative 1, 0, and negative 5, 0. The y values stay the same. I'm not going to be changing that y value. I'm going to have that same y value. And then I'm going to come down. I'm going to have that same y value. And then I'm going to pass back up. So here's our reference graph. I guess it comes a little lower here because it's got to get to that y value. There we go. Okay, and we can see that if we take the red graph and squish it this way, we get the blue graph. And so when I see a number inside the function, f of 3x, I know that's going to be a horizontal compression. And what I'm supposed to do is divide the x's by c. Okay, likewise, if I see f of 1/2 x, that's a horizontal stretch, and I'm going to divide the x's by that c value, 1/2. Okay, so we've got 4 types of transformations now. Let's list them. The first one, y equals f of x plus c. This one was a vertical shift. And how do I carry it out? I add c to the y's. Okay, our next transformation, y equals f of x plus c. This time the number is inside the function, and we know that this is a horizontal shift. And the way we carry this out, inside is opposite land, we subtract c from the x's. Okay, we don't add, we subtract, and we don't do it to the y's, we do it to the x's. Our next transformation, y equals c times f of x. This was a vertical stretch or compression. It was a stretch when c was bigger than 1, a compression for c values between 0 and 1. But what I did was simply, because it was outside of the function, I know it affects y values. I multiply the y's by whatever that c value is. And then our last transformation, the one we just looked at, y equals f of cx. This one was a horizontal stretch or compression. And the way we know it's a stretch is if c is between 0 and 1, and a compression if c is bigger than 1. What are we going to do here? We're not going to multiply. Inside is opposite land. We're going to divide. Not the y's because it's inside. Inside is about the x's. Divide the x's by c. So these are 4 main types of transformations. But wait, there's more. All right, so what happens if we have negative f of x? Well, that's the same as seeing negative 1 f of x. And we know, because of c times f of x, that when we have a number out here, we multiply all the y values by that number. So I want to multiply all the y's by negative 1. What will happen if I multiply all the y's by negative 1? Well, when we go back to our reference graph, y equals absolute x and its reference points, what happens if I multiply all those y values by negative 1 times negative 1 times negative 1 times negative 1? I end up with negative 1, negative 1, 0, 0, 1, negative 1. And what does that graph look like when we make it? Well, we're passing through 0, 0, we're passing through 1, negative 1, and we're passing through negative 1, negative 1. There's my graph. What transformation did we just see? The original reference graph was up here. Now we're down here. So this type of transformation reflects across the x-axis. I know we played with the y values, but what did we flip across? We flipped across not the y-axis, but the x-axis. So when I see this negative out in front, that's going to be a vertical reflection, or reflect across the x-axis. So what if that negative is inside the function? F of negative x. Well, I'm going to divide the x's by negative 1, because inside is opposite land. And what happens when we do that? Well, let's take this f of x. F of x equals square root of x. And here are the reference points. And now I want to divide the x's by negative 1. So if I come back and divide these by negative 1, what do you notice about our new points? This stays 0, 0. This is now negative 1, 1. And this is negative 4, 2. What's my graph look like now? It looks like this. Passing through 0, 0, passing through negative 1, 1, passing through negative 4, 2. Remember, you have to label the points on the graph. It's not sufficient to have them somewhere nearby. Now, what happened to our original reference graph? This was our reference graph. I noticed that it too reflected, but it didn't reflect across the x-axis. This was a reflection across the y-axis, because I'm dividing all the x's by negative 1. And if I have negative f of negative x, that's a double reflection. This reflects across both x and y axes. And I know that because I'm going to multiply the y's by negative 1. And this tells me to divide the x's by negative 1. Great. So now we've got all our transformations. But wait, there's more. So now let's look at a situation like this. We've got y equals square root of x plus 1 minus 2. Now what I like about this function is I've got one transformation inside the function and one transformation outside the function. I know this one will affect the x's. I know this one will affect the y's. I know that inside is opposite land, so this is going to shift the graph left 1, and this minus 2 outside the function affects y values, so the graph is going to shift down 2. And how do I carry out these transformations? No problem. I start with the reference points. See, it really was important for us to know these reference points, or I'm not going to be able to apply the transformations to them. And yes, I do need to see the work. You may not just do this in your head. All right, so I'm supposed to subtract 1 from all the x's. That's what that tells me. And I'm supposed to, because of this, subtract 2 from all the y's. And so my new points, the points on my transformed function, are these. So let's look at our graph. We've got 0, negative 1, negative 1, negative 2. That's where my graph starts, right? There's a hard dot there. And then we draw that square root of x shape. And this must be 3, 0. Okay, so there's our transformation. And it's no problem. I can do one transformation to the x's and another transformation to the y's simultaneously. Great. That's nice. And if I have something like this, y equals 2 x minus 1 cubed. Again, I see this is just a transformation of my reference graph, x to the third. This is inside the function, so it affects x values. This is outside the function, so it affects y values. I know that this shifts right 1, and I know this, because this is bigger than 1, vertically stretches the graph by a factor of 2. How will I graph this? Well, I'm going to start with my reference points. Remember, the reference points for x to the third are these. But I have to carry out these transformations. So this is inside. It affects the x's. Inside is opposite land, so I'm going to subtract a negative 1 or add 1 to all the x's. And then here, I see this c value outside the function attached with multiplication. I'm going to multiply all the y's by 2. So my new points, the points on my transformed function, will be 0, negative 2, 1, 0, and 2, 2. So let's make that graph. 0, negative 2, oops, 0, negative 2, 1, 0, and 2, 2. Now remember, this is not a straight line. I'm not connecting these with a straight line. Instead, this is the x to the third shape. So, looks like a parabola points up over here, and a parabola points down over here. Okay, so I have to know the shapes as well as the reference points when I apply these transformations. Any questions about that? But wait, there's more. So there's one more troubling bit that comes up, and that looks like this. Y equals square root of 2x minus 1, or y equals 2 square root of x minus 1. See, in these problems, I see two x transformations, and in this one, I see two y transformations. And my question is, does the order matter? Oh. So, am I supposed to add 1 to the x's, then divide by 2? Or am I supposed to divide the x's by 2, then add 1 to the x's? Or does it not matter? Either will get me the same graph. Well, it turns out you get two completely different graphs. Likewise here, am I supposed to subtract 1 from the y's, then multiply the y's by 2? Or am I supposed to multiply the y's by 2, then subtract 1? Well, it turns out that the way we know which transformation to do first depends on whether they're y transformations or x transformations. Y transformations follow PEMDAS. So in this case, I want to do the multiplying before I do the subtract. So I want to multiply the y's by 2 and then subtract 1. That's going to be the way I do this. But inside is opposite land. I don't follow PEMDAS, I follow SADMET. So here I want to add 1 to all the x's, and then I want to divide the x's by 2. So not this one, but this one. Wow. So the order does matter. I do get two completely different graphs. So let's go through and try this. So we start off with our reference points for square root of x. 4, 2. And remember, inside is SADMAP, so I have to take care of this before I take care of this. I want to add 1 to all the x's, plus 1, plus 1, plus 1. And that will give me these new reference points, 1, 0, 2, 1, 5, 2. But then I need to come back and do this second transformation, this one here, where I divide all the x's by 2. And so my new graph will be 1 half, 0, 1, 1, 5 halves, 2. We know that the graph was shifted right 1 and then horizontally squished or compressed. So my new graph looks like this. 1 half, 0, 1, 1, 5 halves, 2. Notice I'm not putting any of these on these graphs. Don't. It just makes the problem A take longer, and B, it makes it so that your graph won't be a smooth curve anymore because you're probably not using the same distance between each of these little marks. Draw the shape because you know the transformations, right 1 and squished. Put in the points, connect the dots with the appropriate shape. All right, now what about this one with the two y transformations? So when I have two y transformations, I'm still going to start with those same reference points. Those reference points were 0, 0, 1, 1, and 4, 2 for square root of x, but I see two different y transformations. And I remember that with y transformations, I follow PEMDAS. I have to do multiplying before I do subtracting. So I'm going to multiply all the y's by 2, because outside is all about the y values. And so I get 0, 0, 1, 2, 4, 4. And I can see this point didn't change. There was no shifting of the graph, but this point here is twice as high as that, and this point here is twice as high as that, which means I stretched the graph by a factor of 2. I still have to come back and subtract 1 from all the y's. And so my final points, the points on my graph here, will be 0, negative 1, 1, and 4, 3. So I'm going to graph those points. And remember, that's my endpoint here at 0, negative 1. I draw that square root shape, I pass through 1, 1, and I pass through 4, 3. Notice I'm drawing the shape before I'm trying to label the points, and I'm not trying to line them up with any little hash marks. Woof! All right, so let's take all of this and put it together now. We have a function, 2, 4x minus 5 cubed plus 1. Wow, I got lots of stuff going on here. I can see this is x to the third, so I want to start off with the x to the third reference points. Those are negative 1, negative 1, 0, 0, 1, 1. And what am I supposed to do? Well, I see 4 transformations here. I'm supposed to vertically stretch the graph by multiplying the y's by 2. I see another y transformation here where I'm supposed to shift the whole graph up 1 by adding 1 to all the y values. Then I see 2 x transformations. I'm supposed to add 5 to all the x's because the graph is shifting right 5, but then I'm supposed to come back and divide all the x's by 4 to squish the graph horizontally. So let's do each of those transformations. Outside follows PEMDAS, so I need to multiply all the y's by 2. Inside follows SADMEP, and so I'm going to subtract a negative 5 or add 5 to all the x's. So after one round of transformations, I've got 4, negative 2, 5, 0, 6, 2. But wait, there's more transformations to do. I still need to add 1 to all the y's. And I need to come back and divide all the x's by 4. And so the points on my graph are going to be 1, negative 1, 5 fourths, 1, and 6 fourths, or 3 halves, 3. It's still got the shape of y equals x to the third. Remember that shape. This is our middle point. This is our middle point. So let's make a graph. We've got that one, we've got that one, we've got that one. So this one is 5 fourths, 1. This one is 6 fourths, 3. And this one is 1, negative 1. What's the graph look like? Well, it looks like an up-pointing parabola on this side and a down-pointing parabola on that side. 4 transformations. Now, some students don't want to do 2 transformations at a time. They want to do 1 at a time, because this is kind of confusing and new. So let's do it that way. Okay, I'm going to go through and I'm going to multiply all the y's by 2. And so now I've got the points negative 1, negative 2, 0, 0, 1, 2. And then I need to add 1 to all the y's. And so now I've got negative 1, negative 1, 0, 1, and 1, 3. But I still need to do these x transformations. Remember SADMEP, I have to add 5 to all the x's. And that's going to be 4, negative 1, 5, 1, 6, 3. And then finally, I have to come back and divide all the x's by 4. And so we'll end up with the same points. We'll have just done twice the amount of writing to get there. So I usually like doing 1 x transformation and 1 y transformation at a time. rather than I'm going to do one y and then another y and then one x and then another x. Since the x and y transformations don't affect each other, I can do one x transformation and one y transformation each time I take a step. All right, so now it's your turn. Let's have y equals 1/2 square root 3x plus 4 plus 3/2. Why don't you try graphing this one now? Pause the video, use your transformations to graph this, and when you're done, come back and you can check your answer with mine. All right, welcome back. We see the square root, so we start with those reference points. I really need to know these reference points, I told you. And now I need to apply my transformations. I see two y transformations. Y transformations follow PEMDAS, so I have to multiply the y's by 1/2 and then add 3/2 to the y's. I see two x transformations. I'm shifting the graph left 4 and then horizontal compression by a factor of 3. I need to subtract 4 from all the x's and divide the x's by 3. And I like doing one x and one y at the same time, so I'm going to subtract 4 from all the x's, and I'm going to multiply all the y's by 1/2. So that gives me -4, 0, -3, 1/2, 0, 1. But I still have two more transformations to go. I need to add 3/2 to all the y values. Add 3/2 to all the y values, but I also need to divide the x's by 3. Divide by 3, and I need to add 3/2 to all the y's. And so that's going to give us -1/3, 3/2, -1, 1/2 plus 3/2 is 4/2 or 2, and 0 divided by a number we learned a few days ago is 0. 1 plus 3/2, that's 2/2 plus 3/2 is 5/2. Okay, so what's my graph look like? Well, it's got to have that square root of x shape to it. This is the end point, hard stop. There's my graph, -1/3, 3/2. Something happened. Something happened. Did I subtract 4, -4/3? Okay, there's a 4 there. There we go. And then we have -1, 2, and we have 0, 5/2. Look, I didn't even put in the axes. But if you wanted to put in the axes, you could. Here's x equals 0, so that's the y-axis. And the x-axis is down here, because this number is bigger than 0. Okay, so that's what it should look like. Don't forget to have the appropriate shape and label the points on the graph. Nearby will not work. I will not give credit for that. I will mark that wrong on your homework, on tests, and on quizzes. Now, this is a tremendous amount of information that I've given you today, and don't worry, we've got 3 days of dealing with transformations. So we've got a lot of practice to do, both going forwards and going backwards. And by going backwards, I'm going to give you a graph, and I'm going to ask you to write the equation of it. But that's later. Next, we're just going to practice these transformations like crazy in the next video, and maybe we'll start going backwards, and then we'll pull it all together in the last of these transformation videos. And then we're probably ready for a quiz. So please make sure you take notes on all of this video. Please make sure you know your reference graphs and the reference points and the shapes of those reference graphs, because you gotta know them, or else even if you're doing the transformations perfectly, if you draw the wrong thing through those points, you don't get credit for it, right? So if I ask for cube root of x and you give me x to the third, we may be passing through the same points, but this is what the graph is supposed to look like, and you're telling me that the graph looks like this. And so no, I gotta mark that wrong. All right, so make sure you know the shapes for all these reference graphs, the reference points, and how to carry out all the transformations. We'll practice that more in the next videos and in your homework. Remember, your homework assignment here is number 4, and it's a transformation worksheet. You can find this worksheet in Office 365 under Assignments, under Files, under Graphing Basics. And if you need help finding that, watch the video on our Office 365 main page, or send me a note in GroupMe or email and I'll help you find it. All right, watch this video again. Take lots of notes. Practice. All right, take care. Bye-bye.